Okay, this lesson will run the quickest for you if you have printed off the lesson handout from the Unit 5 tab of our notebook. So everything that you see typed in this document and in this video is already on handout for you. If you have your textbook nearby, the questions I reference will be from your textbook, and I think those are the resources you need with you to make this go quickly. So I changed the title here from Combined Gas Law to the Gas Laws because the Combined Gas Law is really one consolidated version of the other gas laws. And so I thought a better heading is the gas laws. First, we need to look at pressure, temperature, and volume of gases. Be comfortable with the units there and any conversions required. So we recall that pressure of a gas is really the collisions between the particles with each other and the walls of the container. Now, pressure can be measured in a number of different units: atmospheres, kilopascals, millimeters of mercury, torr, pounds per square inch. You'll see the PSI, or pounds per square inch, in the States frequently. The SI unit is kilopascals, and you'll also see atmospheres show up here and there. So I've given you the conversion, so the relationship, conversion factor between all of these pressure units. So if you need to relate atmospheres to PSI, 1 atmosphere is 14.7 PSI, so you can use that in factor label. If you need to relate millimeters of mercury to atmospheres, 1 atmosphere, 760 millimeters of mercury. So having a look at page 543, number 1, in Part A, you're asked to convert 203 kilopascals to millimeters of mercury. So we're going to use the factor label method, just like we've done before, and find the number of millimeters of mercury in those 203 kilopascals. So we follow factor label just like before, set up the units to cancel, going from kilopascals to millimeters of mercury. Now you already know conversion factors easily between centimeters and meters. I mean, this is just the same idea except it's different units. So we see there's 101.3 kilopascals for 760 millimeters of mercury. And so 203 times 760 divided by the 101.3 gives us 1,523 millimeters of mercury. Now, just to be clear, 3 sig figs here, so I'm looking for 3 here, which means I need to make that 3 a 0 to placehold. So 1,520 millimeters of mercury. Okay, so pressure units, just make sure that you convert, and I'll explain as we go through different formulas which units you might need. Now for temperature. If you recall from an earlier lesson, temperature is a measure of the average kinetic energy of the particles. If you've taken physics, you'll recall a formula 1/2 mv squared, where m is the mass of the particle and v is the speed. So how does that connect for us in our gases unit? Well, if we're talking about oxygen gas particles, then they all have the same mass. Whatever speed they're moving at will determine their kinetic energy. And as I said before, temperature is measuring the average kinetic energy of the particles. Not all of the oxygen gas particles will be moving at the same speed, so they're going to have different kinetic energies. But if you have a sample of oxygen gas at 20 degrees Celsius, the average kinetic energy of those particles is being represented by the 20 degrees Celsius. If you raise the temperature to 60 degrees Celsius, you don't change the mass, they're still oxygen gas particles, but that does increase the speed and therefore the kinetic energy, which will overall increase the average kinetic energy. All right, so let's understand temperature units. There's this concept called absolute zero, and I have the figure here from your textbook, page 547, number 3. You'll notice that the y-axis is the volume of the gas, and the x-axis is temperature. Now, temperature in the first set of numbers here has been scaled in degrees Celsius. The dotted points and the solid line, so the solid lines are lines that best fit for the dotted points, which are real data, so experimental data. So in other words, the gas that's represented by blue here was actually cooled below zero at this point, and that was the volume of the gas that it occupied. So if you think of cooling a gas, as the temperature gets lower, it's going to have a lower average kinetic energy, which means the particles are moving slower. And in moving slower, they're occupying a smaller volume. As you increase the temperature, right, we see those particles move with greater speed and greater kinetic energy, and they'll be able to push on the walls of their surroundings and occupy a larger volume. Now, the dashed line for each of these green, red, and blue lines, notice the interesting part here. If you extrapolate those lines of best fit, you end up all back at negative 273.15 degrees Celsius. And so the idea is that at this point, the volume of the gas is zero. In other words, the particles are not moving. We haven't actually been able to cool a gas to this temperature, but the idea is that this is as cold as it gets. We can't get any colder than this for the gas particles because the temperature is the particles' average kinetic energy, measuring the particles' average kinetic energy. And so if the volume of the gas is zero, then the particles are not moving. So they're not occupying a volume. So this is essentially the beginning of the temperature scale. So it'd be nice to call that zero, but it can't be 0 degrees Celsius. That's way up here. So in fact, we call this 0 Kelvin, which is referred to as this term absolute zero. So the Kelvin temperature scale is the temperature scale that we use for all of our gas calculations. Okay, so on page 549, number 1 asks you to convert negative 78 degrees Celsius to Kelvin temperature or absolute temperature. And so we find the temperature in Kelvin by taking negative 78 and adding 273. Notice back here, if you took this negative 273 and added 273, you would get to 0. Same thing here, negative 200 plus 273 would get you to positive 73. 0 plus 273 would get you to 273. And so to change from degrees Celsius to Kelvin temperature, you add 273. And so that's how we will find the temperature in Kelvin. Now, if this temperature in degrees Celsius was given with digits after the decimal, then we would have added the 0.15 here. But I don't need to do that since I'm going to keep the lowest numbers the lowest number of digits after the decimal, which in this case will be none. And so I just add negative 78 plus the 273 and come up with 195 Kelvin. Notice it's not degrees Kelvin, it's just Kelvin. Okay, so all temperature entries into formulas in the gases unit must be in Kelvin. So this needs to become second nature. So all of question 1 is like that. 2 just asks you to go back the other way. So if you're adding 273 to go from degrees Celsius to Kelvin, you'll just subtract 273 to go the other way. By far, the most common conversion you'll be doing is degrees Celsius to Kelvin. So in part C, you see volume. I'll just remind you that if it's a 2-liter flask, then that will be the gas volume, 2 liters. And our units might be liters or milliliters. So you'll see how that works as we go. Okay, so moving into the gas laws. So first law, Charles' law. I've written it out in words, and I want you to think about that with kinetic molecular theory. And I have a picture here, or similar to the one in your textbook. And you'll see that there are gas particles, right, with a movable piston. So this lid is able to move. And there's one weight here applying a certain pressure, which means that these particles are occupying this particular volume, right, moving with the kinetic energy that they have and colliding with a certain pressure. Okay, so how do these two diagrams differ? Well, you'll notice here the increase in temperature. And so if this is considered the lower temperature, right, then this will be the higher temperature. So what's happening? Well, let's notice first of all that with one weight on top of both here, we're creating the same pressure. So the idea is that pressure is constant. Now, what about number of moles? Yep, it's a sealed container, so we're not changing the amount either. So what happens to the volume of the gas as we increase the temperature? We can see a certain volume occupied here, right? And now we can see that there's a much larger volume. So we can see that when the temperature was low, the volume was low, and as we've raised the temperature, we now have increased volume. So now that we see increasing the temperature has led to an increase in volume at constant pressure in moles, that makes sense then to use the terminology that the volume is directly proportional to the temperature. Using kinetic molecular theory, well, as we raise the temperature, we're increasing the kinetic energy of the particles. And as we increase the kinetic energy of the particles, in order to maintain the same collisions, the same pressure, they'll need to occupy a larger volume. Okay, this applies with popcorn. If you think of a popcorn kernel and what that looks like compared to a popped piece of corn, so the actual popcorn that you eat, what's really happening is that we're raising the temperature, and the water that is inside that kernel is then subjected to the increase in temperature, right, which ultimately has that water vapor looking to occupy a larger volume. So why does the popcorn, or why does the piece of corn, the kernel of corn, pop? Well, Charles' law, as the temperature increases, the volume of the water vapor inside the kernel also increases. What does that look like if we represent it in a graph? Well, to have volume versus temperature, we see at low temperatures, so down here, there'll be a low volume, so perhaps here, right? And at higher temperatures, we'll have higher volumes. And so generally, we can set up the general trend, right, that volume varies directly with temperature. Now, volume varies directly with temperature. In order to convert to an equation, we introduce an equal sign instead of the proportionality symbol, and then we introduce a constant. And if you isolate that constant k, you'll see that V over T equals k. And so what we do now to establish a formula for Charles' law is say, okay, well that means that the ratio of the volume to the temperature of a gas at constant pressure in moles always, so that ratio, that quotient is always the same, always the constant. So at a particular volume and temperature, the ratio of the volume to the temperature will be the same constant as the ratio at a different set of conditions. And so this is the formula we use for Charles' law. So let's have a look then at page 552, number 1. Okay, so if you read page 552, number 1, we're looking at a sample of methane gas that occupies 5.25 liters at 200 Kelvin. The gas is heated, so the temperature is raised to 300 Kelvin, and the question is, what is the new volume? And so we're solving for V2. So in this formula here, we need to isolate for V2. So if we start off with V1 over T1 equals V2 over T2, we first need to isolate for V2. So I want to get that by itself. I notice it's being divided by T2, so I'll need to multiply by T2 on both sides in order to set up that T2 to cancel. And that'll leave me with V2 equals T2 V1 over T1, which I'll just flip the sides here so that we can have the unknown variable on the left side. So it's good practice to isolate the variable that you're going to solve for before you substitute your values. Now, before I substitute these temperature values, I better check that they're both in Kelvin. If they're not, if it's degrees Celsius, I'll need to add 273, but these ones turned out okay. And now I notice volume is in liters. Well, if it's liters there, then it means that V2 will be liters. If volume had been milliliters, then the volume of the new volume would also be milliliters. So it doesn't have to be liters here. It's just going to be the same. V1 and V2 will have the same units. So we substitute our values and solve. Okay, so you'll see that I substituted my values, computed 7.875 liters, and because I had 1 sig fig with these trailing zeros here, I go to 8 liters as the final answer. So the only trick with questions like this is to make sure that if the temperature is given in degrees Celsius, that you first convert to Kelvin. Okay, moving on to Boyle's law. So where Charles' law kept pressure and moles constant, Boyle's law keeps temperature and amount constant. So we're looking at what happens when you change the volume and pressure of the gas. So how do volume and pressure relate? And if you have a look at the diagram on the right here, you'll see where the pressure is low, right, at a constant temperature, these particles are moving with whatever kinetic energy they have, and with few collisions here, they are occupying a larger volume. Whereas there was one weight on this movable piston, and so these particles have to counteract the weight of that one block. Now if we have two weights, right, we've increased the pressure here. That's why it says high gas pressure. And now you can see what's happened to the volume. So we can see that we're now occupying a lower volume. So if increasing the pressure leads to lower volume, then do pressure and volume vary directly or inversely? Well, hopefully you're thinking inversely. That's right. Okay, so looking at the process of breathing, inhalation and exhalation, just to familiarize yourself with the key anatomical parts. We've got the trachea here, so when we breathe in through our nose or our mouth, this is your windpipe where the air passes through, and then the trachea splits into each bronchus, and a network begins here of bronchioles, but generally we're into the lungs. So we have two lungs. Now there's a muscle, your diaphragm, that's below the lungs. Okay, so the key here is that there's a pathway for air to come in and out of the lungs. We have the two lungs and the diaphragm, this muscle. So in inhalation, so when you inhale, your diaphragm contracts, so that muscle contracts. Now what happens to the size of the lungs as this diaphragm contracts? It's essentially pulling down here and creating more space for the lungs. So because we have an increased volume now inside the lungs, that's going to drop the pressure inside the lungs. Now I've labeled them one in each lung, but it's happening in both lungs. Now because there's a lower pressure outside compared to the atmospheric pressure, the atmospheric pressure is higher than what's inside the lungs, then on inhalation, the air will rush into the lungs. So that's when you breathe in, inhalation. Now on exhalation, the diaphragm relaxes. So you can see it curve up here. And in doing so, that's going to actually decrease the volume of the lungs, both lungs, and in doing so increases the pressure inside the lungs compared to the atmospheric pressure, the pressure of the air in the room you're standing in. So when the pressure is greater on the inside, now the air will flow from the high pressure inside the lungs to the lower pressure outside. So this is the process of inhalation and exhalation, how we breathe, and that's how Boyle's law factors in. Now, in terms of a graph of volume and pressure here, because they vary inversely, when one of them is low, for example, the volume, the pressure is high. When the volume is high, then the pressure is low. So you can see we set up this negative slope or this inverse relationship. Now, we saw over in our diagram here that this volume, V1, right, was at a low pressure, P1, and we ended up having a lower volume, V2, at a higher pressure of P2. And so what's the relationship here? Well, we said that volume varies inversely with pressure. So if we multiply on both sides, then we'll have PV is directly proportional to 1 here. Now we want to introduce an equation, an equal sign. So there's the equal sign and the constant. So now I can say for two different sets of conditions, P1V1 will equal P2V2. So the product is the constant, and so we can relate two different sets of conditions. So check out page 559, number 1. Okay, so helium gas has a volume of 8.25 liters at 446 kilopascals. What pressure must be applied to the gas when it occupies 12 liters? So we can see that the volume is increasing. I hope you're expecting the pressure, the final pressure then, to be lower than what we started with, that inverse relationship. So we go to our Boyle's Law formula here, P1V1 equals P2V2. Go ahead and isolate P2, then substitute and solve. In terms of units, just check that your volume units are the same. They're both liters, that's great. Whatever the pressure units are, kilopascals, that will be the unit of P2. Okay, and so I isolate P2 by dividing by V2 on both sides, and substitute and solve. Now noticing that the measurement here of 12 liters, V2 has 2 sig figs, I'm going to round the 306.6. The 6 will bump the 0 to a 1, and I place hold the 1's position with a 0. So final answer, 310 kilopascals. Okay, third law, and the final one before we put them together, is Gay-Lussac's law. And you can see by this data here the temperature is changing, and so is the pressure of that sample. So we notice as the temperature is increasing, the pressure is increasing. So both variables are changing in the same direction. At constant volume in moles, temperature and pressure vary directly. We can see an application of Gay-Lussac's law with car tires and tire pressure in the winter. We have the same number of moles of gas in our tire, but as the temperature drops, the kinetic energy of the particles drop, they move slower, and they are, in order to occupy the same volume, as they're moving slower, they're going to collide less often. So when the temperature drops, the pressure drops, and that's why people will find that they sometimes need to put more gas into more air into their tires in the winter. Okay, so drawing a graph of P versus T, this is going to be very similar to what we did for V versus T. When the temperature is low, so is the pressure. They vary directly. When the temperature is high, so is the pressure. So we end up with a graph like this. Saying that pressure varies directly with temperature leads us to convert to an equation with an equal sign and a constant, and then P over T equals K. And so now we can say at two different sets of pressure and temperature conditions, we have this relationship. So this is the mathematical expression of Gay-Lussac's law. Having a look at page 559, number 3, you're being asked or being told that soccer balls are typically inflated to between 60 and 110 kilopascals. So if a ball is inflated indoors with a pressure of 85 kilopascals at 25 degrees Celsius, then taken outside, where the temperature on the playing field is negative 11.4 degrees Celsius, what will be the pressure of the gas inside? Okay, and so we list all of our values here, converting degrees Celsius to Kelvin. Now, just to be clear here, there were no digits after the 25 degrees Celsius, so I didn't worry about having digits after my 273. No digits here. I'll make sure there's no digits in the Kelvin temperature, no digits after the decimal. For T2, they gave it to me to the nearest tenth of a degree Celsius, and so I made sure to have the 0.15 of the conversion to Kelvin, and then I rounded my answer to have one digit after the decimal, which corresponds to the lowest precision here in T2, one digit after the decimal. So we have P1, T1, and T2 need to solve for P2. So isolate P2 and substitute and solve. Okay, so I'm going to multiply by T2 on both sides in order to eliminate the T2 here, and that leaves me with P2 equals T2 times P1 over T1. So that's the formula I'm going to use to solve for P2. Okay, you'll notice that I brought P2 to the left and moved all of this to the right and substituted my values. I rounded to 2 sig figs because of the 2 sig figs in P1. I did not use the 2 sig figs from T1 in degrees Celsius. I followed the rules for adding, came up with 298 Kelvin, and when I plugged that in, now there's 3 sig figs here for this multiplication and division. So 4, 2, 3 means I'm going to round to 2 in the end. Okay, final piece to this lesson. So thanks for hanging with me here. We learned that in Charles' law, volume varies directly with temperature. We also learned in Boyle's law that volume varies inversely with pressure. So let's put those together, that volume varies directly with temperature and inversely with pressure. And now I'm going to multiply on both sides by pressure so that I can say that PV is directly proportional to T. Now you might notice that Gay-Lussac's law is also in here now, right? Pressure varying directly with temperature. Okay, so I want to write this now as an equation. So PV equals, now I have to introduce a constant. Isolate that constant, and I have PV over T equals K. So for two sets of conditions then, P1 V1 over T1 equals P2 V2 over T2. And this is essentially then the combined gas law. Combined because if you have a look back in your notes, you'll notice that Charles' law is contained here. With Charles' law, pressure is held constant. So if you ignored the P1 and P2, you just have V1 over T1 equals V2 over T2. That's exactly what we wrote for Charles' law. For Boyle's law, when temperature is constant, we'll just ignore it, cover it right up, and we have P1 V1 equals P2 V2. That's exactly what we had earlier in the lesson. And for Gay-Lussac's law, you can see it still on the screen, right? Volume is constant, so if we ignore volume, V1 and V2, then P1 over T1 equals P2 over V2. So in fact, if you learn the relationship here for the combined gas law, then all the other formulas we did in the lesson can basically be read right from here. So when you read the question, if they tell you pressure is changing and temperature is changing and they don't mention volume or they don't say that it's changing, then just ignore the volume and work with the Gay-Lussac's law equation. And similarly for Charles and Boyle's law. All right, so what happens in a question where all three are changing? Well, let's look at page 560. Okay, so page 560, number 1, describes a balloon at the top of a mountain and at the bottom. And at the top of the mountain, you're given the pressure, volume that the balloon occupies, so the volume of the balloon, and the temperature in degrees Celsius. You're asked to find the pressure at the bottom of the mountain if the balloon has a volume of 825 milliliters and the temperature is 15 degrees Celsius. So pressure is changing, volume is changing, temperature is changing. We'll need to use the combined gas law. We will be solving for P2, so you'll need to get rid of the V2 and T2 on that side. And be careful, make sure you always change to Kelvin temperature. So that should be automatic when you're listing your given. So you can complete the conversion to Kelvin, isolate for P2, and go ahead, substitute, and solve. Okay, so I've added on 273 to get my Kelvin temperature. Just to show you how I isolate P2, I will multiply on both sides by T2, which will cancel it on the right side. And now I have V2 in the way, so I'll divide by V2 on both sides, and that will get rid of V2. So ultimately what I finish with here is P2 equals T2 times P1 times V1 over V2 times T1. And so we discover that the pressure at the bottom of the mountain is 102 kilopascals. All right, so basically all of the questions done today can be done using the combined gas law formula. The P1 V1 over T1 equals P2 V2 over T2. The keys to remember are that these temperatures here must always be in Kelvin, and you need to be good at isolating variables. If a variable is not changing in the question, then just omit it, and that'll lead you to Charles, Boyle's, or Gay-Lussac's formula. Okay, good luck with that.